Quite often, when you are going to solve a problem, it might become easier to solve this problem in a different set of coordinates. We are all quite familiar with the most common way to change your coordinate system. An example for it may be when you go from Cartesian coordinates to spherical coordinates. This kind of common transformations are called point transformations. And more in general, they could be expressed as a transformation where you pass from qi, so a general position, to a new position that is a function of the previous positions. And the same thing for the momenta, where you pass from the previous expression of the momenta to a new expression that is a function of the various momenta of the system. This is something we all have done in any kind of physics course, and it's how you usually consider a transformation. Of course, when you do this kind of transformations, the Hamilton's equations don't change. The form of the equations doesn't change, so we don't lose all the advantages of using the Hamiltonian approach, the Hamiltonian formalism. For example, even the evolution in time of a system could be considered a point transformation, because of course the new position will be a function of the previous position, and new momenta will be a function of the previous momentas. But in the Hamiltonian approach, there is another kind of transformations called canonical transformations that are able to go in a more generical way. So during a canonical transformation, the Hamilton equations will still have the same form, but we will pass from the coordinates to a new coordinate that is both a function of the positions and of the momenta. And the same thing, of course, for the momenta, where we pass to a function of positions and of momenta. This transformation is called canonical if the Hamilton equation doesn't change its form. So under this transformation, this must still hold true. The Hamilton equation must stay in the same form. Of course, as these new momenta and positions aren't really momenta and positions anymore because they are a function of both, they are usually simply called canonically conjugated quantities. But they're still written usually as Q and P. In order to understand what I should impose to a transformation in order to be canonical, we have to go back to what we have seen about the Lagrangian. That if I have two Lagrangians that do only differ by a total time derivative of a function that only depends on positions and time, they will give you the same equations of motion. So we can write it in this way. Of course, as we are now working in Hamiltonian mechanics, we have to retransform this in a Hamiltonian. Thus, doing some passages that I will skip, we arrive in saying that the Hamiltonian, so the Lagrangian, must be equal to the same thing but in the new coordinate set minus the new Lagrangian plus, as said, the total time derivative of this function. This function, that was written small letters here, this function is called the generating function, and we will see a little bit better why it's called like this. So the differential of this generating function can be expressed as pi dqi, so the old coordinates, minus the same expression in the new coordinates, plus h first minus h dt. From this, we can in the end find how we can put together the new and the old coordinates. In fact, the old momentum is equal to the derivative according to the old positions of the generating function. The new momentum is equal to the partial derivative according to the new position of the generating function. And in the end, h first is equal to h plus the partial derivative of f depending on time. Actually, these conditions can be written in a more concise way using the Poisson brackets. So, if I have a Poisson bracket between two functions in the old coordinate system, it must be equal to the Poisson bracket of the two functions in the new coordinate system. So the Poisson brackets are invariant under canonical transformations. Thus, we will again have the old rules of the Poisson brackets. They will be still valid for this new set of coordinates. So, we can simply impose the fact that the Poisson brackets should remain the same, and there should be the same rules that we had with the old set of coordinates. The canonical transformations aren't always of big interest when solving practical problems, as many other things in the series, in this part about Hamiltonian mechanics, but they're quite more interesting actually on a theoretical point of view. We'll see it better in the next video.